Hi, this is Miss Fitzmars, and this video is an example of how to solve heat, work, and energy problems. So just to recap from last time, our main idea is that sigma E minus sigma E naught, which is the change in energy, is equal to heat plus work. And we know that work is F parallel delta X, so this is work. The force has to be a quote-unquote useful force or an intentional force. So, for example, tension, F pull, Fn if you're lifting something. Those are all intentional forces. Okay, specifically not Fg, F spring, F from friction, or F air resistance. Okay, F friction and F air resistance cause heat, so we have Q equals minus F parallel delta X, and this could be from friction or from air resistance. And the reason we don't count Fg or Fs is that they are already represented in our conservation of energy, or in the change of energy, as Ug, the gravitational potential energy, and Us, the spring potential energy. And so to keep track of those, we would be double counting them. And the last bit is that power is equal to work divided by time. And remember that power is in watts. Okay, work and heat are both in joules because they are changes in the energy of a system. Alright, so what I want you to do is I want you to pull out the sheet you got today that said energy, work, and power practice problems, number 2. So number 2 says, Maggie is pushing her egg baby in a stroller. Okay, we know that that has a mass of 100 kilograms. And we know Maggie is pushing with a force of 50 newtons. Okay, so Maggie's arms make an angle of 45 degrees with the ground as she pushes the baby. So we know our angle is 45, and she pushes the baby a distance, that's our delta x, of 100 meters. And so we want to know a couple things. First of all, we want to know how much work she did. Second of all, we want to know how fast will she be going at the end. And finally, we want to know if she lets go and there's now friction, how far will the carriage go before it stops. Okay, so when we're solving these problems, kind of like when you solve conservation of energy problems, you need to draw before and after pictures. And I'm going to draw like time A, time B, and time C. Okay, in time A, Maggie is just starting to push the stroller, and this is the stroller, and the stroller is at rest, so their initial velocity is 0. In time B, she is pushed between A and B. We know that it's gone a distance of 100 meters. And in time B, she's pushing the stroller, and they're going some speed. We don't know what speed. Okay. And then finally, at the end, she lets go of the stroller. It goes some other distance, and we want to know that in part C, and it comes to a stop again. Okay, so it always helps to draw out the picture. We might not need it for part A, but we will need it later on. Okay, and so in part A, we want to know what is the force acting, or we want to know what is the work. Okay, and we know that at work is equal to F parallel times delta x. Okay, and F parallel is like the part of the force parallel to the movement. And so if we look at the forces acting on this carriage, and I'm going to draw a force body diagram on the side. Okay, we have Maggie and she's pushing down at 45 degrees. We have FG, so I'm going to say this is F push. And then we have Fn from the ground pushing back up. We know that F push in total is 50 newtons, okay, but the total is always our hypotenuse. Now, if she's moving from side to side, and it seems like she's pushing this thing along the ground, then we are looking for the side-to-side component, or we're looking for F push X, okay, and that will be our F parallel, okay. Now, just to refresh your memory, this is adjacent to our 45-degree angle, so F push X, or F parallel, since it's adjacent, will be F push times cosine 45 degrees. Okay, so we're going to go ahead and we're going to put that into our work. We have work equals F push times cosine 45, and then our delta x, the distance it has been pushed, is 100 meters. And if you multiply that all out, you should get work is equal to, remember you plug in 50 for F push, so 50 times cosine 45 times 100, and you end up with 3,536, and the unit is joules. Okay, in part B, it wants to know how fast she'll be going by the time she gets to the end. Okay, so for this, we know that speed has to do with kinetic energy. So that tells us we probably need to think about how the energy is changing, and we need to use this big equation, sigma E minus sigma E naught equals W plus Q. Okay, and so we go back, and we're really talking about A and B. We want to know how fast she's going by time B. Okay, and just like we did when we did conservation of energy, we're going to list what kind of energy does she have at the beginning. And actually, there's no energy at the beginning, so sigma E naught is equal to 0. And at the end, she's not up at a height, so sigma E, the final energy, is equal to her kinetic energy. Okay. In between, we have the heat and the work. And so we know there's work, and we actually calculated a number for that. But there's no heat because it says there is no friction. Okay, so I'm going to take this information and I'm going to include work is equal to 3536, and I'm going to bring it to my equation. Okay, so I have, remember, there's no energy at the beginning, so sigma E was 0, and I have only kinetic energy at the end, so I have K minus 0 equals, I know there's no heat because there's no friction, And I know that work is equal to 3536 joules. Okay. So I'm going to go ahead and remember from eons ago that kinetic energy is equal to 1/2 mv squared. So I have 1/2 mv squared is equal to 3536. I know the mass of the stroller is equal to 100 kilograms, so I have 1/2 times 100 v squared equals 3536. Okay, I'm going to divide both sides by 50 because 1/2 times 100 is 50. I get v squared equals 70.7 meters per second. And then finally, I take the square root of both sides, and I get that the final velocity is equal to 8.4 meters per second. And that'll be my answer to part B. In part C, it wants to know if Maggie lets go, and now there is suddenly friction, maybe it got to a rough part of the pavement, and there's a friction force of 35 newtons, how far will the carriage go before it stops? Okay, so we have Maggie, and she lets go. We know that at the moment she lets go, our velocity is equal to 8.4 meters per second. And then we want to know how far she'll get before the carriage totally stops, so the final velocity is 0. Okay, and so we're using this picture right here as our before, the instant she lets go, and our after picture is the instant the carriage came to a stop. And now we can go ahead and we can use sigma E minus sigma E naught equals Q plus W. Okay, we know that after she lets go, she's not applying any force, so there's not going to be any work. And we know that in general, our heat is equal to negative F parallel, and we know the friction force times delta X. Okay, we also know, if we look at our before and after picture, that in our after picture, it's not moving, okay, because our velocity is 0. Okay, our object is not up at a height, so there's no UG, and so at the end, sigma E, not sigma E naught, just sigma E has to be equal to 0, because it's not moving. At the beginning, sigma E naught is going to be kinetic energy because it's moving. There's no UG at the beginning because this thing is not up at a height, and there's no spring involved. Okay, so I'm going to plug this all into my equation. I have 0 minus K equals minus F parallel delta X. Now I have two negatives, and that will give me a positive. Okay, I'm multiplying both sides by -1. And for K, I'm going to fill in 1/2 mv squared. And I'm going to say that's equal to the absolute value of F parallel times delta X. Now, at this point, we can get rid of this absolute value sign. Okay, because we know we're solving for delta X, and we're going to need to divide by the force if we have something positive over here, and we know the size of the friction. As long as we make that positive, we'll get our correct delta X. So we're going to plug in the numbers. We have 1/2 the mass is 100, V is 8.4, so squared, and that is equal to the force from friction, because remember, friction is stopping this thing, that's causing the heat, and we know that's 35 newtons, and we're solving for delta x. Okay, so finally it's just down to the algebra. We have 1/2 times 100 times 8.4 squared, and we get 3536, and that is equal to 35 times delta x. We divide both sides by 35, and we end up with delta x is equal to 101.02 meters.